Okay, this is the residual plots lesson. So I'm just going to go through these notes that I was going to have us do in class. There's a link on the assignment if you want to print this out and go through these notes too, but you don't have to. So we're going to start with what is a residual, and that's on this left side over here. So it says a residual is the vertical distance from the point to the line of best fit. So the line of best fit, that's just another name for our regression line. So regression line, line of best fit, those are the same thing. So on number 1, it says, what is the approximate residual for the point 3, 7? So if we look at this graph, we have 1, 2, 3, and 5, 6, 7. So we're looking at this point right here, and we're looking at how far away it is from that line, from our line of best fit. So on this one, the residual is about 1.5. It's about 1.5 units away. So we would say that the residual there is 1.5. The next one says, what is the approximate residual of the point 4, 2? So 4 is here, 2 is there. So we're looking at this point. So the residual on this one, it's below the line. So we would say that the residual is -1 because it's just one grid line down from our line of best fit. And then the last one, what is the approximate residual of the point 9, 8? So 9 is here, 8 is here, so that our point that we're looking at is right there. And remember, we're looking at how far away it is from the line, but in this case, it's right on the line, so the residual would just be 0. Okay, so that's what a residual is, and our lesson is on residual plots. So what we're going to do is we're going to look at how far away each point is from the line, and that'll tell us if the regression line is a good fit or not. So the second column says, what is a residual plot? A residual plot is a graph that shows all the residuals on the vertical axis and the independent variable on the horizontal axis. So we're just plotting these residual values. If the graph has a strong correlation, so this is a strong correlation, and it's linear, so right here it says linear, that means that the pattern is a line, it's not curved, it's not like an arc, like a rainbow or an exponential curve. It's not like that. It's saying that the data has a strong linear correlation. The distribution of the residuals around the x-axis is random. So this random part is really important. And then it's also tight, which just means that it's close to the line. So if we look at this graph down here, the points right here, they aren't very far away from the x-axis. That's what this is saying is this is our regression line. That's the x-axis. And then we're taking our points, and it's kind of like just putting them on there like this is the regression line. And it's telling us how far off of the line it is. Okay, the next one says a weak linear fit. The distribution of the residuals around the x-axis is random, but loose. So if you look here, these points are pretty far off of that x-axis, which means that the correlation is weak and the line of best fit, it's a good line, but it just means that the correlation is weak, so the points are really spread out. But in either case, if it's a random distribution, or the points are randomly spread, like these two are, then that means that it is linear. So if it's a random, if the points are random, that means that the line is a good fit for the data because the data is linear. The last one says nonlinear. So right here for nonlinear, it says the distribution around the distribution of the residuals around the x-axis is not random. So if you see something where it's not random, that means that your data wasn't linear to start with. So here you can kind of see that this follows a curve. So that means that it is not linear. So what we're doing in this class is we're only doing linear regression. So if you see something that's curved or it doesn't look random, then that means that it is not linear. And so a regression line would not be a good fit. So a linear regression is not good here. Because if it's curved like this, if the residual plot is curved like it is here, it tells us that the data wasn't linear to begin with. So we shouldn't do a linear regression. We should do some other kind of regression. Okay. Another type that shows that the regression is not good is if we have a plot like this. If all of the points are above the line like that, this is also not good. Because the points should be evenly spaced above and below the line. So like this. The red would be a good fit, would mean that the regression line is a good fit. If you have a bunch of points that are above the line or a bunch of points that are below the line, then that's not good. Or if it's curved like this. Okay, and then the third column on this set of notes is an example. So this says the line of best fit for the scatter plot is below. So this is the regression line. And if we were given the data, we could plug that into Desmos and we could find M and B, which you're going to have to do on the test review and on the test. So this is our M from Desmos. This is B from Desmos. If we were finding this ourselves. Okay, and then we can see that the line goes through the points. There's some on this side, there are some on this side, so it should be a pretty good fit for the data. What we're going to do is we're going to calculate the residuals. So when x is 1, the y value here is 2. So I'm going to zoom this out a little bit. When x is 2, the y value here is 3. When x is 3, we have 2 and 5. So I'm just looking at these points. So this is 1, 2. This point is 2, 3. This point is 3, 2. This point is 3, 5. And you won't have to find the y values on the review and on the test. I just give you these. So I'm going to finish writing this down, and you should write this down as well if you printed off these notes. So this one is 4, 6, 5, 7, 6. Oh, I missed one. This is 7, 6, 8, 8. So those are the actual. Now we're going to do the predicted. So we're going to take this number and plug it in for x and then figure out what it would be. So I'm going to go to the scientific calculator on Desmos. So on here, our first one, we have 0.74 times 1 plus 1.4. So that tells us that the residual there is 2.14. So this is 2.14. Then I'm going to go back, or sorry, the predicted value there. I said residual, but I meant predicted. So according to our regression line, the predicted value is 2.14. So now I'm going to go back to this, and I'm going to type in 2 instead, and that tells me right over here that this is 2.88. And then I'm going to do it again, but this time I'm going to do 3. So that's 3.62. Both of these are 3.62 because both of the x values are the same. I'm going to erase these red dots. Okay, so that's how we do that. The next one would be 4.36. Then we have 5.1, 5.84, 5.84, 6.58, 7.32, 7.32, and then our last one is 8.06. So we have our actual here, and then we have what our regression line predicted. So the difference between those two, that tells us our residual. So what we're going to do here is we're going to take the actual minus the predicted. So on the first one, we're going to have 2 minus 2. I'm going to make my ink a little smaller so that it writes easier. So we're going to have 2 minus 2.14. So 2 minus 2.14, that's just negative 0.14. On our next one, we're going to take 3 minus 2.88. You can do that in your head or you can type it into a calculator, but that would be 0.12. Our next one, we have 2 minus 3.62. That tells us that the residual is just negative 1.62. Then we have 5 minus 3.62. That residual is 1.38. 4 minus 4.36 gives us negative 0.36. 6 minus 5.1 gives us 0.9. 5 minus 5.84 gives us negative 0.84. 7 minus 5.84 gives us 1.16. Then we have 7 minus 6.58. That would be 0.42. Then we have 6 minus 7.32. That gives us negative 1.32. 8 minus 7.32 gives us 0.68. And then our last one is easy. It's 8 minus 8.06. So that gives us negative 0.06. So now we have all of our residuals calculated. So it's not the whole equation, it's just this part. That's what we're using to graph. So down here, our residual is going to be, this is the x, and then this is the residual that we just found. So when x is 1, right here, we know that the residual was negative 0.14. So negative 0.14, that's going to be pretty close to the line. Maybe even a little closer. So 0.14, that's pretty close to 0. The next one, x is 2, and the residual was 0.12. So I'm going to put it pretty close to the line as well. The next one, we have two values. We have two residuals where x is 3. So the first one was negative 1.62. That would be about right there. And then the other one is 1.38. So I'm going to put it about right there. Then we have x is 4. That's negative 0.36. That's about right there. Then we have where x is 5, we have 0.9. Where x is 6, we have negative 0.84 and 1.16. When x is 7, we have negative 0.42. When x is 8, oh wait, that one was positive 0.42, sorry, positive 0.42. When x is 8, we have negative 1.32, so that's about right there. We also have another one, which is 0.68, so I'll put it about right there. And then our last one is negative 0.06, so I'm going to put that right next to the line. So this is our residual plot. So based on what we talked about over here, how would you describe the residual plot that we just did? Is it a strong linear fit, weak linear fit? Is it nonlinear? So look at this and decide what you think about this based on the residual plot. On here, we can tell that the points are random, so we know that it is definitely linear because the points are random. There's a few above and a few below. It's not curved or anything like that. And if we look at our examples, weak means that the residuals are really spread out. Strong means that they're pretty close to the line. So on this one, I would probably say this is a strong linear fit. And that is how you do regression plots.